Contrary to a conventionally sized UAV, the concept of a swarm attack includes many micro or mini UAVs that work together to attack a specific area all at once. The concept was first introduced in the late 80s, and the thought was that anyone that controlled the swarm of UAVs was afforded the chance of having a multitude of advantages. The key obstacle at the time, however, was the programming sophistication available to engineers at the time. But now, with current programming sophistication, algorithms have been written that allow for up to 100 UAVs to accomplish what is known as autonomous flight. A heterogeneous swarm of UAVs, which is what will be designed in this project, is one where micro or mini UAVs in a swarm of hundreds may look alike, but they can be split up into groups to achieve different missions simultaneously. The Swiss SMOVNet project was born of the idea of sending out many mini UAVs to a site requiring assistance ahead of human personnel. This may include scouting a building out before firefighters try to save lives, or even locating victims of natural disasters. The drones in this case would be surveillance, search, and rescue drones with a mission profile consisting of mainly a launch, dash, search, and a return home stage. Recently, the United States Navy has introduced the LOCUST project, and the Army has introduced the PERDEX project to work on swarming technology. The existence of such swarming technology could almost be seen as an unfair advantage over the enemy. Advantages include allowing for multi-mission operations all at once, larger surveillance areas being covered simultaneously, more enemy vehicles being engaged simultaneously, you having the upper hand of psychological warfare since you'll be overwhelming the enemy, and as well as spending less money than on a conventional UAV. Following the call for a weaponized swarm, it was decided to design for military application. In order to design a highly competitive swarm attack UAV platform, the three very best UAVs in the market were analyzed. These include the PERDEX drone, EB, as well as the Skywalker X6 drone. The competition analysis led to a PRS aimed at achieving the best performance that could be given. The UAV is required to have maximum speed greater than 60 knots, maximum acceleration greater than 2 Gs, perform attack, kamikaze, and surveillance missions, and as well as achieve a 30-minute loiter time at the very least. This is to be achieved under the constraints of a maximum launch altitude of 25,000 feet. It should be capable of a sky launch, and the dimensions should be no bigger than a mini UAV. Criteria is heavily performance-based, with things such as low mass, best endurance, best range, ease of manufacture, and low cost, just to name a few. To ensure that the very best aircraft configuration was developed, 4 completely unique concepts were designed with enough detail to compare against the performance-based criteria. These included a quadcopter, tail sitter, flying wing, and a gull wing concept. Comparisons show that overall, the flying wing would be the best option due to its superior range and endurance, least number of parts to join together in manufacturing, least complex manufacturing process, and as well as its power usage, which was found to be very efficient. The flying wing was thus developed further. Considering that the aircraft will be in a mission requiring both attack and defense, it was decided that the dash speed of the aircraft would be the design point of this project. Seeing as the maximum speed is directly affected by the specific excess power, the SEP equation was manipulated so as to give a procedure that helped obtain the required wing reference area. The procedure was as follows. First, a form of propulsion was chosen. Then, the altitude of flight was chosen. A CD0 was assumed. An Oswald's factor was assumed. And finally, the aspect ratio was varied until the right reference area was found. After optimization, it was found that the best aspect ratio was 5, giving an SREF of 0.038 square meters and a wingspan of 0.435 meters. In the high-level design phase, two main challenges are what stood out, the first being recoil energy. Now for something such as the Thunderbolt, which is basically a flying machine gun, the bullets are no more than 2% of the total aircraft mass. Here, something like recoil forces are of absolutely no consequence, and engaging in firepower actually looks a little something like this. In the case of a mini UAV, however, the bullet fired can be as much as 10% of the total aircraft mass, and recoil forces become something of a real big concern. If not properly handled, it could actually start looking like this. To solve this problem, conservation of energy and conservation of momentum equations were employed to find the thrust required for UAV to reduce speed by no more than 5 meters per second. It was decided that the firing speed would be 26 meters per second and the thrust required would be found to be 1.6 kilograms. The chosen motor had to fulfill these requirements. The next challenge was ensuring that the aircraft was stable in both the longitudinal and lateral direction. Using XFLR5, whilst fully aware of the limitations, the stability and trim conditions of the UAV were analyzed. The UAV was found to be longitudinally stable, but laterally unstable in terms of Dutch roll and slow spiral modes. This was due to the complete lack of yaw damping caused by the absence of a vertical fin. To counter this, it was decided to add rudders to the winglets of the UAV. Once analysis was complete, the final configuration of the UAV looked like this. As shown, the UAV makes use of a 3-blade propeller, has inboard single-slot flaps, outboard elevons, an optical payload, and Rofus rounds as ammunition. The complete specifications are as follows. The mid-level design phase focused on detailed wing design. The structure of the wing included 2 tapered spars as well as 5 mm thick ribs all along the wing. An FEA analysis that was checked against hand calcs was used to ensure that severe loads shown anywhere in the VN diagram were fully supported. Considering that the entire swarm is meant to be as inexpensive as possible, it was decided that 3D printing was the route to go. When it came to material selection, PLA was found to be the filament of choice due to its biodegradable nature, lack of fumes during printing, as well as mechanical properties which made it ideal for this application. The real challenge, however, was figuring out how to 3D print the entire wing as a single part when it had overhang parts which would require the nozzle to deposit filament in mid-air. The Autodesk Mesh Mixer software was used to design printing supports which fixed the problem. The combination of using off-the-shelf components such as servo motors, cameras, bullets, and batteries, together with 3D printing the entire airframe and using friction welding to join parts together, led to a total hardware cost of the UAV swarm being 2.44% of the total cost of a conventionally sized UAV. This means that over and above the possibility of multi-mission operations, covering larger surveillance areas, engaging with more enemy vehicles, and having the upper hand in terms of psychological warfare, the military saves up to 97% on the total cost for hardware alone, where you would usually spend much, much more. Many advantages come with these savings in cost. Firstly, part of the money saved can be put to use in the form of humanitarian aid. This allows the military to be of more help to countries that have been hit either by natural disasters or countries that were casualties of war. They can also give greater support to organizations such as Doctors Without Borders and Engineers Without Borders. It also gives the state the power to make military personnel earn better and take care of their families, funding their children's education and ensuring health care for all the personnel. All to better thank the men and women that bravely lay their lives down to protect their respective nations. Switching to the swarm attack UAV option means a win not only in times of war, but in times of peace as well.